I think we can start. So I would like to welcome all of you to this second Al-Kindi Distinguished Statistics Lecture. It's a pleasure to see so many familiar faces, but also visitors outside of KAUST coming from Jeddah. So I'm going to tell you a little bit about this lecture. The Al-Kindi Distinguished Statistics Lecture, an annual event in statistics at KAUST. We have a distinguished guest speaker who is invited to present a series of 2 lectures and remains in residence for some days. So the first lecture, this one, is intended to demonstrate to a general audience the breadth of use of statistics in applications. And the second lecture, at 4 p.m. today in the MPR room, is intended to a more specialized audience, although everyone is welcome, of course. So the lectures are named after Al-Kindi, a prominent figure in the House of Wisdom, whose book, entitled Manuscript on Deciphering Cryptographic Messages, is believed to be the earliest writing on statistics. In his book, Al-Kindi gave a detailed description on how to decipher encrypted messages using statistics and frequency analysis. So this text arguably gave rise to the birth of both statistics and cryptanalysis. So today I'm very pleased to announce that the second Al-Kindi Distinguished Statistics Lectures are going to be presented by distinguished Professor Noel Cressy from the University of Wollongong in Australia. So let me tell you a little bit about Professor Cressy. He's the director of the Center for Environmental Informatics in the National Institute for Applied Statistics Research, Australia. He's a professor of statistics and a distinguished professor at the University of Wollongong. He's also adjunct professor at the University of Missouri. He received his Bachelor of Science with honors from the University of Western Australia and an MA and PhD from Princeton University. His past appointments have been at Flinders University of South Australia, Iowa State University, and the Ohio State University. So Professor Cressy has published in the areas of goodness of fit, statistical modeling, empirical Bayes and Bayesian method, remote sensing, spatial and spatial-temporal statistics. He has co-authored 3 books, authored or co-authored 3 books, one in 1988 on goodness of fit, one in 1993 on spatial statistics, and one in 2011 on spatial-temporal statistics with Chris Weichel. It's actually a book that we use here also in the class on spatial statistics. So Professor Cressy is the recipient of the Committee of Presidents of Statistical Societies 2009 RA Fisher Lectureship, of the Statistical Society of Australia's 2014 Pittman Medal, and the Royal Statistical Society's 2016 Barnard Award in Environmental Statistics. He's a fellow of the American Statistical Association, a fellow of the Institute of Mathematical Statistics, a fellow of the Spatial Econometrics Association, and an elected member of the International Statistical Institute. He's a very highly published and cited researcher with many more accomplishments than time permits to mention here. So with the Al-Kindi Distinguished Statistics Lectures, we would like to recognize Professor Cressy's outstanding achievements in statistics, and particularly in spatial statistics. So please join me in welcoming Professor Noel Cressy to the Al-Kindi Distinguished Statistics Lectures.
Good afternoon, everyone. First of all, thank you so much to the statistics group, particularly Mark Denton, who had invited me some time ago, and we had a schedule for last year to give this second Al-Kindi lecture, and I had to cancel at the last minute. Unfortunately, I hate to do that. I've rarely done that, but I'm here, and I'm very happy to be here and to see what a wonderful crowd you are, and I look forward to some questions at the end. First of all, can everybody hear me at the back okay? Yeah, good. So it's a wonderful lecture room, and the acoustics and the facilities are fabulous. So, all right, so that's where we live. This is our planet. There aren't many planets like this, although somebody discovered a cluster of them. Unfortunately, it'd take about 300,000 years to get to a planet that's very close to this, that can support life as we know it. So my point is, it's all we've got. And a very important part of our planet is water and carbon and dust and various other things. But I'm going to concentrate on carbon and the carbon cycle. This particular cartoon is from the Intergovernmental Panel on Climate Change, the latest one, and it just shows the carbon cycle. Things get into the atmosphere, they come out of the ground, they come from the atmosphere back into the ground. We think of fossil fuels as powering our energies, less so now because we have alternative, cleaner sources of energy, but nonetheless I think we're hooked for the moment on carbon-sourced power and energy, and our economies certainly would falter if we didn't have it. We're trying to transition away from it. And the Earth has got all the carbon it's ever going to have, and we can't do anything with it. We might try to ship it into outer space. That has been suggested as a rather radical form of getting rid of carbon, but let's just say for the moment carbon is cycling in our system, and that system has different clubs that are in motion. And the Carbon Club is one of those, and it's spinning, and up until about 200 years ago that club was spinning, got caught and thrown up in the air again, and everything seemed to be working just fine. In the middle 19th century, 1850s, we went through an industrial revolution, steam engine. James Watt invented the steam engine. It was driven by coal, and since then we've had combustion engines based on coal, gasoline, petrol, oil, and gas, and they're all carbon-based. So the point is that we're actually extracting carbon from the Earth, and we're putting it into the atmosphere. As I said, there's a cycle, and carbon is tending to stay more carbon is staying in the atmosphere than before. And in fact, we were at about 280 parts per million in the mid-1800s, and we just passed 400 parts per million last year. That's official. There are people who measure this, not just at single sites, but there are people who come up with global values for carbon. It mixes in the atmosphere rather well. So after carbon is emitted from your different sources, it ends up mixing rather well after some time, after several months, on the order of 3 months. Those molecules that are coming out of the Earth's surface tend to mix quite well. There are other things that, other clubs that are spinning, the aerosol club, the cloud club, if you like. But the carbon club is the one that I think we have to be really concerned about. Certainly to understand the climate cycle and the climate system, we need all clubs. But the carbon club is contributing to global climate change and warming because carbon in the atmosphere, carbon dioxide, is a greenhouse gas. It's not the only greenhouse gas, but it's the most important. I'm not saying it's the most powerful, because methane is about 20 times more powerful than carbon dioxide, but there isn't as much of it in the atmosphere. But carbon dioxide, due to its presence in the atmosphere, is the most important greenhouse gas, and our Homo sapiens, our particular genus and species, are putting that carbon into the atmosphere at a great rate. We've heard about treaties like COP21 that happened in Paris, where countries have signed on to sort of decrease the amount of carbon they're putting in, or probably to decrease the amount of increase, if you like, to decrease the acceleration of carbon, and to eventually, return carbon to values that we believe that the Earth system can absorb. Okay. Here's a 3-number summary. I'm a statistician, so I like numbers, and these numbers are sort of quite telling. So the general agreement is that our Earth system can handle 2 degrees Celsius increase in temperature. And if you reverse engineer that, you end up needing to reduce the amount of greenhouse gases in the atmosphere. That increase in temperature is largely caused by greenhouse gases, and so one has to think about how we might decrease the amount of carbon coming into the atmosphere based on this 2 degrees Celsius threshold. We're at about 0.9 now, since that 2 degrees is beyond the Industrial Revolution. We're at about 0.9 now, heading for 1 degree increase, and we're sort of feeling some effects even at 1 degree increase. I think, I don't know, where I live in Sydney, we just had the warmest summer on record, and that broke the previous summer, which was the warmest summer on record the year before, etc. And that's been for the last 4 years. And you can sort of go around the world and find instances of evidence, shall we say, of climate change that's starting to become potentially problematic. More cyclones because of warmer oceans, and warmer oceans means more water vapour being taken up in the cyclonic or hurricane world, and you end up with more of them. They come earlier. There are ways also to measure climate change through blossoming of flowers, through spring times coming earlier. There's just a lot of evidence that our world is in a state of climate change and in general climate warming, and there's some feeling that even at 1 degree we're having trouble to mitigate and eventually maybe to adapt. So 2 degrees is like an accepted number, but it was just pulled out of the air. And the feeling was that if everybody did what they said in Paris in 2015 for COP21, that we would reach that 2 degrees around middle of this century, and it would level out. But everybody has to agree. It's non-binding, and you know, my personal opinion is that we're headed for 2 degrees and beyond, and it looks like even at 1 degree we might be in a bit of trouble. So that number is just a baseline that a bunch of climate scientists chose, because I think, my personal opinion is because they thought it was achievable. And that number was chosen about 15 years ago. What's more likely from my study on regional climate models is that number might be more like 3 to 4 degrees. Certainly my studies in North America show that in northern Canada and northern United States, that temperature increase in the winter will be on the order of 4 to 5 degrees. So 2 degrees is somewhat optimistic. The other number is basically what it would take for us to burn, how much carbon dioxide should we put into the atmosphere to reach that 2 degrees by mid-century, and it comes to about 565 gigatons. And the third number is how many gigatons of CO2 equivalent is in the ground, or about to be, or ready to be exploited. And my last question is, will companies leave it there? Because when you do the maths, it's 5 to 6 times more than it would take to reach 2 degrees by the middle of the century. I think the answer is probably no. These are very profitable companies, and if they agreed up front to leave it in the ground, their share price would plummet, because, I mean, it's carbon, it's in the ground, you're not going to touch it, right? So then why you're in business? So there's a point to make there that this isn't just a climate problem, it's a financial problem, and it's, well, as a society, we're really we're a carbon concentration society, and we haven't yet made the transition to alternative energies, although there are some people who are out there trying. All right, so just to continue on for a little bit of stats, carbon dioxide is actually very long-lived in the atmosphere, and I've got a little distribution here of 100 molecules. About half of them will be removed within 30 years. And if you go down the bottom, 20% or so will still be in the atmosphere in a few thousand years. It's a very long-lived gas. So you might even argue, as some have, that we're already locked in. No matter what we do, if we stop using carbon, stop putting carbon dioxide in the atmosphere, independently of COP21 and the Paris Peace Accords, we are headed for 2 degrees and beyond because we have more carbon in the atmosphere than our Earth system is able to handle. So this carbon club that I'm talking about is spinning. It's not spinning in the same way it used to do 200 years ago, and there's a general feeling amongst some that the club has already been dropped, that we can't catch it. And that's the image I'd like to leave with you. So there's, yearly increases of atmospheric carbon dioxide have been about 2 parts per million per year for about 30 years or so. This is accelerating, actually, probably borne out by the fact that these carbon dioxide molecules stay in the atmosphere for a long time. And I mentioned before that we just hit 400 parts per million. The last time we were at 400 parts per million was 3.6 million years ago in the Pliocene era, and Homo sapiens were not on this planet at that point. So we are in new territory, is my message here. All right, I want to point out there is an origin down here, right? This is 320 parts per million. If you go down 0 parts per million, there has to be carbon dioxide in the atmosphere just due to natural processes, photosynthesis and such. But the number in the pre-industrial period was 280. So it's not all that far down here. 280 is down here somewhere. And this represents what's happened to us in terms of parts per million from 1960 through to about the present time. And it looks linear, except doesn't look linear. After a while, it looks like we're in some sort of quadratic increase of carbon dioxide. The black line is a moving average, which just to give you some idea of the yearly increases. The red line is the sort of oscillation that you expect due to drawdowns of carbon dioxide in the spring as photosynthesis takes place, and then outgassing later when there's ploughing and burning and various things. The actual, apart from the seasonal influences, this increase, one might say that it's our fault. And let me say why that is. Things are in roughly equilibrium, pre-industrial. As much carbon was going into the atmosphere was coming out again. It's often absorbed by the oceans. It's taken up in wood. It's taken up in photosynthesis, so there are natural systems that take it up. Lately, about half the carbon dioxide that's been going into the atmosphere has been due to us, been due to these anthropogenic processes, if you like. In fact, some people call this current period the Anthropocene, right? So a little joke, but it's basically, we haven't been on this planet all that long, and we've been doing our best to change it in different ways, sometimes for the better, sometimes for not the better. And we need to seek a balance, and I'll put to you that we don't seem to see a balance, certainly in carbon dioxide. This is the measurement from the famous Mauna Loa Observatory on Hawaii that was started in the 1960s. And thank goodness we have this to sort of scare us a bit. So I've already talked to some of this, but the important thing is to go ahead and start measuring carbon dioxide. And the Mauna Loa Observatory does that, and it does it in one place. And it's really measuring the ambient carbon dioxide. It's not getting at something that I'm going to not mention, but really talk about today, which is where is this carbon dioxide coming from, and hopefully how can we sort of absorb it back into the Earth system. And as I mentioned, photosynthesis does that, and we end up with carbon in wood. Unfortunately, when we get forest fires, the wood burns and carbon's released in the atmosphere. When we burn fossil fuel combustion engines in our cars and in our factories and our coal fire burning, coal-fired power plants, we end up putting it back into the atmosphere. So what we need to do is to get a more local view of where carbon dioxide is being absorbed, and then we call that a sink, and where it's being emitted or outgassed, and we call that a source. So we're trying to get and that happens essentially at the Earth's surface, because once it comes in the atmosphere, it's moved around by winds and various meteorological processes. So we're trying to get a hold of sources and sinks at the Earth's surface and trying to map it, essentially. And the reason is because if we know where it's coming from and we know it's really bad there, we can do something about it. So that cartoon that I showed you of the carbon cycle has no spatial component in it at all. And it has arrows indicating a temporal or dynamical component, but we don't know where. And if you don't know where, you don't know why often, and you don't know how to do anything about it. So Mark gave me a very generous introduction, which I appreciate, and he mentioned that I work in spatial and spatio-temporal statistics, so I'm going to get onto that in a minute. So this is NASA. The instrument that I'm particularly interested in, and I'm on the science team, NASA's science team for this, is the Orbiting Carbon Observatory 2, the OCO2 instrument, and it is NASA's first dedicated satellite measuring carbon dioxide. There are other instruments that indirectly measure carbon dioxide, but OCO2 was launched for precisely the science reason that I just mentioned, trying to work out where carbon dioxide is emitted or outgassed and how it's absorbed into the Earth system. This is my rocket. There is about, I don't know, 300 or 400 people who look upon it as their rocket, but it's mine. I don't have a share in it or anything. Let's just say I put a number of hours into working out how to do statistical analyses from the data from this rocket. But to put a rocket up into space like that takes several hundred people for many thousands, each one many thousands of person time. And in the end, you're talking about an incredible effort to get that rocket up. So this is a picture of the rocket. It's just been launched from Vandenberg Air Force Base on the west coast of the United States in California. And it goes into a low Earth orbit. You can see somebody actually took this a long way away, up in California actually, in the San Gabriel Mountains, way north. MECO is main engine cutoff. So it goes into a low Earth orbit and the main engine's cut off, and then this fairing separation occurs. That's a good sign, by the way, because the fairing is what protects this very delicate instrument, and it goes through all sorts of vibration and all sorts of violence to get up there, and then if all goes well, this fairing separates and the instrument is pushed out into orbit very gently. And that's a picture, a cartoon of what the instrument looks like with its solar panels helping it fuel what's happening up there. And it's possible, of course, to fire up. It has rockets that will enable it to go into higher orbits or lower orbits. And I think it went into maybe 200 or 300 kilometre orbit, and eventually it's now at a 700 kilometre orbit in a train of satellites. Actually back here, there's a train of satellites that it's in called the A train, A for afternoon train, and it's like a minute apart from two different satellites, one in front of it, one behind it. The one in front of it measures aerosols, and aerosols are really important when you do these calibrations to work out how much carbon dioxide there is in the atmosphere. So this is for the stat people here, and it's really about uncertainty quantification. And there's a deep philosophical question here: is if we've got a sample of size 1, which is our planet, how can we possibly do any statistics? And let's just say we have ways. We think about spatial statistics and replication within space, pseudo-replication if you like, and we think about time and things being very similar from one time to the next or one day to the next. So we work hard to come up with replication and ways to estimate what's happening. But what we're trying to do is look for a probability space. And here's what happens. This particular satellite orbits the Earth 14 orbits a day, and it takes about 16 days to produce all those orbits. It only ever looks, it's a passive instrument, so it only ever looks during the day. I mean, it's looking at night, but there's no signal. So we're only ever seeing daytime. But the Earth is rotating, so actually you get a complete picture of the Earth after 16 days. It returns to the same orbit and repeats, and hopefully stays up for a long time. This particular instrument's been up for about 2.5 years, and it's performing as hoped, with a few small exceptions. But every now and then there has to be some kind of retracking of the orbit to avoid space junk, or there's a little slippage in the orbit, so it has to go back up into the A train. So there are all these sorts of wonderful engineering things that I think are great. I'm a rocket scientist wannabe, but I'm just a mere statistician, and I love to hear about all this stuff that's happening. Not that I can do much about it, but I just hear about it. So what we're trying to do is use really probabilities. Yes, sorry, you have a question. Yeah, I'm just trying to separate it out. There isn't anything special about that. It's actually a very narrow orbit. If I were to draw this in proportion to the orbit, you would not see those lines. So its footprint is on the order of 2 or 3 kilometres, and each orbit is on the order of 100 kilometres apart. So, you know, there's just big gaps. A lot of people think that remote sensing, everything's cool, have a great geometry, you know, spatial statistics should work beautifully because I see data everywhere. In fact, it's not true. You have large gaps between orbits, and you have very narrow paths often. And then the orbit geometry is different depending on the altitude that the satellite's flying. The higher it is, the longer it takes to get around the Earth. So there's lots of interesting things, different satellites at different orbits. Yeah, that's just more for illustration. So I'm going to put to you that we can use probabilities. We can think about, and I'll show you some, we can think about using Bayes' theorem to come up with optimal estimates of the carbon dioxide in the atmosphere. So OCO2 is the polar orbiting. I talked a little bit about, you know, its features. It turns out that there is no thermometer, there's no thing hanging off this satellite saying, oh, right, so that's how much carbon dioxide there is in the atmosphere. What happens is that this is the complete cycle. This is sort of your question, but the non-cartoon question. These data, every point here, the data associated with one of those points, and I think there are probably about 100,000 here, looks like that. That's, in a sense, a datum, a multivariate datum. This is a spectrum in 3 different channels where we're looking at a weak CO2 band, a strong CO2 band, and an oxygen A band. And each one of those contribute to carbon counting of molecules in a column from the Earth's surface up to the satellite flying at 700 kilometres. It's amazing that you can actually get this sort of precision. But these instruments are amazingly sensitive and amazingly precise. And as you can imagine, there's a certain amount of noise associated with it. So just to repeat here, one of these dots, any one of these dots, I have to use 2,000 observations at different frequencies. This is in the infrared part of the frequency, at different bands in the frequency to come up with one of these dots. So computing time is really important, and I'll talk a little bit about how you go from this 2,500 to 3,000 dimensional vector to come up with one number. I'll talk a little bit about that in a minute. But if you take 8 minutes to do the computing from 3,000 observations to come up with one number, that's too long. But that's what it took about 5 years ago, 8 minutes. And then gradually people started to refine the whole process, and we're down now to about 2.5 minutes maximum. And it would be great if they could do it quicker, obviously, because they could process more data. In the end, they really only process about 10% of the data. And part of that is due to computing, and some of it's also due to various clouds and aerosols getting in the way. As I said, there's a passive instrument. That means the sun is reflected off the surface of the Earth and it goes up to the satellite. And there are a lot of quality control checks that keep throwing out various bits and pieces of the data. The harvest rate is between 7 to 10% of all possible soundings that happen. Okay, so this is one retrieval, right? One of those dots. And as I mentioned, this vector is on the order of 3,000 dimensions. There's a state underneath that vector, which is typically on the order of 50 dimensions. And most of that state is sort of important because it's adjusting for the state of the atmosphere. It would have aerosol component in it, would have an ice component, it would have temperature components, it would have a number of components at different geopotential heights that adjust for the state of the atmosphere. And there are 20 components in there, in that Y, that tell you the carbon dioxide in parts per million at 20 different geopotential heights. The problem is they're very, very highly correlated. So what people often do is and as you can imagine, if you're looking down through a column of the atmosphere, it's really hard to retrieve what's happening at 20 heights. Probably the best you can do is retrieve what's happening at an integral or an average of what's happening at the 20 heights. So you can get one number out, and that dot here, that dot is that number. And it's called XCO2, and it's an integration or an average over the 20 possible values of carbon dioxide that exist in this state vector. Anyhow, the state vector is on the order of 50 dimensions, and I have 2,000 to 3,000 dimensions here. Unfortunately, this function f, which is a way to convert the state of the atmosphere into radiances or energies on the camera, unfortunately that's a nonlinear function. In fact, it's highly nonlinear. It's more like linear and exponentials of the y's. And so what a lot of kind of our distribution theory and statistics does great for linear, but not so well for nonlinear. So this is where being a Bayesian sort of helps, because behind y, there's actually an idea of what the atmosphere should look like, right? This is the true value of the atmosphere, and behind that is a prior mean and a prior covariance of the atmosphere. I call it a process model, but the literature on retrievals in the atmosphere calls it a prior, okay? So basically, we're going to use Bayes' theorem to come up with an optimal estimate of this thing I called XCO2, which is the dry air column average CO2 mole fraction. It's essentially the average of those 20 values that are retrieved in the atmosphere. So that's the target, but what we actually see is kind of that noisy version of y hat, and I'll talk about the process that gets us y hat in a minute. But what people generally do is do a plug-in, and then they get something called X hat CO2. And it's important to keep apart what your target is and what your data tell you, because there's notions of bias and mean squared prediction error when you're trying to get to your target, but you have this imperfect set of observations. So it's a good idea to just look at what might happen for the linear model. And if you had a linear model, it turns out you can solve that problem without doing any iteration. It'll take, I don't know, a second or a microsecond or a nanosecond to come up with an optimal estimator. So that's assuming that F is mu plus Ky, but it's not. And as a consequence, there's an algorithm that's used called the Levenberg-Marquardt algorithm, known to us in statistics. Marquardt was a statistician. Levenberg was an applied mathematician. They independently discovered this algorithm, but essentially it's iterative. And that's why when these numbers are retrieved, that one dot might take 2.5 minutes, is because a starting value is chosen and then an iteration. They're looking for a mode, basically, a posterior mode. We call it a posterior mode. They'll call it the minimum of a cost function. But they're looking for the posterior mode of this distribution. And the nonlinearity is what stops this iterating in one iteration. And it also stops the distribution of this optimal estimate y hat being Gaussian. Even if you have your error process being normally distributed in Gaussian, the final result is not Gaussian. Anyhow, so importantly, there's a Jacobian at the back of this, and that Jacobian has occupied my time for the last 5 years because I'm interested in its statistical properties as well. Okay. So our target was XCO2, and we're going to use the estimate X hat CO2, which we get by integrating the estimates of the carbon dioxides at 20 geopotential heights. And then we use an S hat, which is a linear approximation or a delta method, to tell us what the variability is, or the mean squared prediction error is, of X hat CO2. So all of that, somewhat standard, except this F, this forward function, is nonlinear, and it causes some trouble. So I'm back to my picture of these, this repeat cycle that happens, and I'm going to collect them all together. I'm going to make sure I know where I took the observation and when I took the observation. And now I'm going to call that whole data vector Z sub D to distinguish it from the Z that I use for any individual retrieval. D for data, right? So I've taken a bit of time to get here, but I've got a few sort of, I can speed up a little bit, but I want to get to this point where this is what the satellite gives us. And we've already, gone to some function of what's happening in the atmosphere. So we've integrated it. We've got what's called the column averaged carbon dioxide. And that's, if you like, that's it. Yes. Lower. Yeah.
Where there is like most of the
Right.
Amazon and the
Right.
African basin. The fact that there is more absorption of CO2
Yeah.
there. Why is that?
Well, there's a strong seasonal component to carbon dioxide. You saw it in the Mauna Loa site, and I think way back I give the dates, 16 days.
Summer.
Yeah, there we go. Yeah. It's 801 to 817, right? So the springs, we're done with the spring. There's no drawdown. We're into the summer, and I guess there's some decomposition starting. There's also another feature which I think you were hinting at, or maybe not, but there's a reluctance to retrieve anything down here, basically because the solar zenith angle is at a very poor angle, and you get very poor signal to noise ratio. This is a southern hemisphere winter, I think. Yeah. So there's all sorts of seasonal effects that occur here, and there's also a latitudinal effect, which means that basically carbon dioxide is generally speaking, when you average over the whole year, is lower in the southern hemisphere than it is in the northern hemisphere. There's a strong latitude. It's not in this particular one because of the way this is summer and winter. But there are a few kind of physical things that we know about carbon dioxide. If we were to go back to the spring and we're looking at, if we get a decent look at at the Amazon. We never do because of clouds, right? Africa, you know, tropical Africa and Amazon are very hard to get decent data on. But when we do, and if we have ground-based observations, we tend to see in the spring drawdown and lower carbon dioxide values. So the data that's coming out of the Orbiting Carbon Observatory doesn't contradict anything we know about the carbon cycle. And as you can see, it gives us very good spatial information and on occasion sort of notorious gaps that we see in the Earth system, but that's life. Most of this is due to clouds and aerosols, the gaps. So the science objective, as I mentioned before, is to come up with not those pictures, that's OCO2's objective, is to provide those data to carbon cycle scientists. The science objective is to do an inverse modelling problem and work out where the carbon dioxide comes from, given that's what you're looking at. And also knowing things about, well, where people live, how much carbon dioxide they produce, where power plants are, basically to try and drill down into very local processes. So I do spatial statistics, and one of the methods I use, one of them is kriging. And so I'm going to show you what I can do with those data to smooth out the noise, right? So this is pretty noisy. I've got lots of gaps, and I'd like to come up with a map. And that map I would then like to use to come up with the science objective. So kriging basically, sorry, I'll go back here. Kriging takes the data and takes a linear combination of them. It's very simple, but to come up with the optimal weights that you put on the data can be hard when you've got lots of observations and you end up, you know the equations you want to solve, but you end up having difficulty because of the size of the data sets. So we're often into big data, big spatial data problems. And I've been worried about that for the last, I don't know, probably 9 or 10 years, worrying about how to come up with this inverse matrix that for the particular data set that I've got is probably 200,000 by 200,000, and I need to take its inverse, right? So that's why I featured it in red. I know these weights are optimal, statistically optimal, and I know I'm going to get better mean square prediction errors if I use them. My problem is I don't know how to compute this for a large matrix. So I'm not going to dwell too much on this, but I have worked on this for the last 9 or 10 years and come up with a method that I call fixed rank kriging. And it's a way to take inverses of 200,000 by 200,000 dimensional matrices by making certain assumptions about the underlying covariance structure of the model. And I don't have time to go into it. But let's just say there are papers, and I'd be happy to talk to you about it later. So this, we keep looking at this, right? This is our picture. This is what NASA have done with data of this sort. And they've done some form of kriging, not my type of kriging. They've made much more egregious approximations, and they come up with a map of what these XCO2 values should look like over the whole globe. And this is a different period, I want you to note. It's sort of 3 or 4 months after the launch of the satellite, 4 or 5 months after. But that's a typical picture, and it's called an L3 map. L3 meaning level 3. This is called an L2 map. L2 means level 2. And these sort of data that I mentioned before, they're called L1 data or level 1 data. So you can see gradually when you go from different levels, you end up, in a sense, expanding your picture to a point where you hope you can interpret it. I'm going to redo this map, and I'm going to do it for every day in 2015, using these very fast computational methods that I mentioned. But before I do that, we're very interested in what we're doing now is to project the data not on lat long grids, but on hexagons, because hexagons are equal area tessellations on the Earth's surface. And if you're doing with a per unit volume measurement, you want to use equal area or equal volume tessellations. So basically there are ways to do this, and there's an icosahedral projection of Earth's surface. This concentrates on North America. There's another one that concentrates on other parts, Africa, and I think Australia sort of sneaks in on one of them. There's Africa. So you can put these surfaces and tessellations, they're diamonds really, on the Earth's surface, and then flatten it, right? And so why would you do that? Well, first of all, you want equal area, and if I put hexagons inside this flattened icosahedron that are equal area, then I can start doing this type of stuff. This is a fancy soccer ball, right? Anybody play soccer here, football? If you do, you know that there's a pentagon sort of spread around the soccer ball, and then there are hexagons. So we can basically do change of resolution with equal area hexagons in a consistent manner. And that's what we do in this particular form of kriging. Whereas NASA didn't do that. NASA are hooked on latitude and longitude, and I'm trying to get them off that drug a bit and get them onto hexagons. And it's going all right. There are people who are willing. So these pentagons that I mentioned, they're still there, but they're much, much smaller. And I only need 12 of them, and the rest are equal area hexagons. So basically what I do is I use those hexagons inside the flattened icosahedron, and I do my kriging essentially in 2 dimensions, using nearest neighbour routines that were written by a guy at JPL called Tim Stow. There's a little bit of filling in needed, so that there's a bit of repeating needed, because in here I need to know that, you know, Australia, Tasmania is near Australia, and New Zealand is near Australia, and various things. And if you're in one of these kind of gaps, or gords they're called, if you're near a gorge, you have to make sure that you can repeat and find nearest neighbours. So this is a picture of once we put those predictions back on the globe. This is the sort of picture you would get of carbon dioxide in the atmosphere, XCO2 in the atmosphere. So that's the sort of thing I'm going to do. Rather than sort of hiding half of the Earth and just showing you part of it, I'm actually going to put it on a lat long display, but I want to assure you that that work was done on the hexagon, and that's important. So this is too much information. What I want to do, this is sort of describe how we did it with fixed rank kriging in space and in time. And what I want to do is show you, although we did it for every day in 2015, I'm going to choose the 1st of January, the 15th of January, the 1st of February, the 15th of February. I'm going to choose the 1st and the 15th of each month and just give you a little kind of idea. But we can do it for every day, and we have done it for every day. And we actually have a YouTube video which is available where you can see the whole year that's done for every day, and there's a movie, obviously, it's why it's on YouTube. So there's the 15th of January, 1st of Feb, 15th, 1st of March. By the way, the bottom one, you know, if you're interested in XCO2, you'll look at this top one. The bottom one is the uncertainty quantification, the square root of the standard errors. There's something interesting that happens over here, right? The instrument, I mean, it looks like you have no certainty at all, yet somehow or other you have a map. The map's not brilliant, and there's a lot of averaging going on, and in fact that's what happened. The instrument turned off for about 2 weeks. And so you might say, how the heck did you get in? And it turned off sort of at the end of April into the middle of May. And how the heck did you get a map when you didn't have any data? Well, I have a space-time dependent process, and I'm able to get a map, but I'm also able to say, don't trust that map. The map, in a sense, looks for days in the past and in the future, right? Because we're doing this not in real time, but we're doing not a filtering exercise, but a smoothing exercise. We look in the past and the future for spatial dependence, and we can compute Kriging weights that respect how far apart they are in space and how far apart they are in time. This one's interesting, and you can see there's strong structure here on what happens over land versus what happens over the ocean. And when you go back, you find that for these particular orbits, the instrument really spent a lot of time over land and not much time over ocean. And you're able, the engineers and rocket scientists are able to point the instrument, and they were doing experiments over what they were getting back in terms of reading over land. So during that period, most of the time the satellite was pointing at land and not at ocean. And you see that is reflected by the standard errors. Okay. We're basically in the last part of the talk, and this is sort of the surface flux process, and I'll spend a very brief amount of time on it, but this is where the science is headed. And I have a project at University of Wollongong where we're deep into this work, but I'll only spend a short time on it. What we want to do is solve an inverse problem, and I'll show you the idea behind it. Remember XCO2, it's what the satellite sees. The flux process, Y sub f, is what we'd like to get a hold of. And what we see is determined by the flux process transported by a matrix B, which is a transport model. And it's essentially meteorology that will take us from carbon dioxide molecules coming out of the Earth's surface and staying in the atmosphere. And that particular transport matrix B depends on time as well, but I haven't featured it right now. So the data are these estimates of X hat CO2. The underlying process is linked to the thing that we don't observe at all. We only observe an indirect measurement of it. B is not a square matrix, it's a long, narrow matrix. So there's problems with information. So the whole process revolves around essentially minimizing two terms, a sum of two terms. One is trying to express fidelity to the data, and the second term is a regularization term that we would call a prior distribution. And if you took e to the minus a half of all of this, then what you've got is the data model times the prior model. The rocket scientists don't tend to think that way. They think about, oh, how close can we get to the data? And then we need to regularize because I know roughly what the prior mean is and what the prior covariance is. So the first term we've talked about, in fact, I spent 45 minutes in this talk talking about the first term, not so much about the transport model. The second term is where there's a lot of action and a lot of interest. And people come up with models about what the contribution is of carbon dioxide fluxes, and those models drill down into cement factories, into road systems, into trees and photosynthesis, and what the ocean, the air, atmosphere exchanges are. They're very local and very global at the same time. So there's an attempt to really come up with the physics of how fluxes happen at Earth's surface using these particular models, and that informs on the prior mean and the prior covariance. Yes, there's a question.
How do you account a model?
Yeah, they're in there too. Yes, we've got a guy on our science team who's Mr. Volcanism, we call him. He's a German guy, and he's sort of all over it. And so volcanism, volcanic eruptions, are really important, a source of carbon dioxide and aerosol for that matter, but certainly important. So yes, it goes down to the city level. We have a sub-team looking at cities, local areas, volcanism. The cities, of course, contribute because of factories and roads and different things like that.
But the second term does not seem to have a time.
So so it's buried, that's the big matrix, right? Sorry, it's a big vector, YF. So the time component is in YF. So what you do is you just keep concatenating and you're accounting for it in the prior mean because there's time component in the prior mean. Just as in the transport model, that's a big matrix and big vector, you're accounting for it there as well. But that's a good question. Where's the time component? It's in there. So basically, we're back to the future now, and I'd like to close that we have greenhouse gases and we want to understand them. If we get to a point of mitigation, then this work that's where it's headed. If we get to adaptation, our lives will change. That's what adaptation says. We have to live a different life. And 2 degrees is an attempt to keep us within the mitigation strategy and not into adaptation. And there's a small plug here that this sort of work might also help in treaty verification. And I think we better get on with it because our future depends on it. Okay, so thank you very much. I'm happy to take questions.
So we have time for some questions.
If you, I mean, you can certainly use the mic, but if
It's a short question. Well, first of all, how do you calibrate the instrument? How do you know there's measuring?
Yeah, so it's a good point. I have another part of my research program. So the question is, how do I calibrate the instrument? These instruments, you know, they're flying at 700 kilometres and it's a really hard problem. I made that point. There are about 25 surface measurement stations called TCON, the Total Carbon Column Observing Network, and they measure every minute, every 2 minutes, from a period of around 10 a.m. to around 3 p.m. when they get really good signal to noise ratio with the sun. So we get really good time series of 25 locations around the planet. And they're used to calibrate the instrument. OCO2 is on version 7, which means there was a version 6 and a version 5 and a version 4. We're headed for version 8, and every time we do a new version, we make sure that it lines up with these TCON stations, because calibration, I mean, otherwise you're just hoping for the best. And I do know, because I was involved in this early on, before, around version 2, they were off by about 7 parts per million, which is huge. And then, of course, there were adjustments made, physical adjustments. But let's just say this whole process is a work in progress. But early on, unless you have some gold standard like TCON, you don't know that you're off. And TCON was telling them that they were off by 7 parts per million early on. Right now, the target is to stay under 1 part per million out of 400 parts per million. That anything above 1 part per million is considered a failure. So this is a really very precise attempt to be really precise with the measurements. Thank you for the question, it's really important. Yes, Meredith.
Great talk, thanks. Quick question is there was the filtration step essentially, which produces the stuff that you then use fixed rank kriging to produce maps for. Are any of the uncertainties that come from the first step showing up in the maps in the second step, and sort of what is the proportion of uncertainty? What's the scale for the uncertainties from the first step versus the kriging type uncertainties?
I think everybody heard that because it was in a microphone. So these uncertainties are based on the actual fixed rank kriging. And the general feeling is that it's called S hat, and it's somewhere back here, that the S hat that is produced is off. There's something not right back on the individual, you know, one of those dots where you recreate, and I'm going to find it in a minute. There we go. This S hat here, it's off. It's off by a factor of 2. It's too small. And part of the reason is because there's a strong nonlinearity of the forward function, and the S hat uses a delta method, what we call a delta method, and that delta method, as you know, assumes linearity, sort of local linearity. So I've published a paper on this in the Journal of Geophysical Research where I do one extra step of the delta method, and I show that I'm able to get a much better approximation to this S hat, to the mean squared prediction error than S hat. People don't like using this, and I'm going to fast forward again, sorry about this, but it comes up here in the very last part. See this? That's often used, but there's a lot of grumbles about using it. It's often used in this very first term here. See this? It's used in there, and it's off, which basically means the posterior mean has a weight on it that ain't right. What we do with kriging is we use the internal variability of the data to tell us what that term is. So we don't use S hat. And that's already an advance, I believe. I haven't demonstrated that to the satisfaction of everybody on the planet, but that internal variability is much more accurate than the S hat that's used from the retrieval. And the reasons are, I think, due to this linear approximation and delta method.
We take one more question from Mohammed here.
Hi, so if I understand correctly, for each column we have measurements at different heights, correct?
It's possible. The variability associated with them is huge.
Okay.
But for each column you get 20 measurements, and mostly it's averaged.
Okay. So it's averaged, but I imagine, for example, and correct me if I'm wrong, that at a different height that's further from the satellite, you might have more uncertainty in the measurement than one closer. Is that taken into account in the averaging? Or?
Yes, it is.
Okay.
Yes, it is. So make sure that happens. That's part of my job, actually, because the weights that are used in it's a weighted average, and the weights are very important depending on what the geopotential height is. There are a lot of observations near the Earth's surface into the mid-troposphere, and then not many as you go up higher in the atmosphere. And those weights are used, the variance of a linear combination of data is, and that linear combination might be H, it's often called H primed X. The variance of H primed X is H prime sigma sub X H. And those H's are very important when the variance is calculated. Yep.
Right, so if there are more questions, please, you can ask after the seminar.
Sure, I'm here.
But before we close, we have a gift souvenir of
Okay.
this occasion that will be offered by the Dean.
Thank you very much.
Thank you
for coming.
very much.
Thank you for coming.